All right. The central sort of idea of chapter 19 is the scientific revolution and the Enlightenment. Two things that actually build on one another. You can't really have the Enlightenment without what goes before it, which is the scientific revolution. The first part of the chapter that you'll be reading will talk about why does this begin in Europe, and the textbook goes through several reasons why the scientific revolution begins in Europe. The Europeans will manage to take information they have gained from China, contact with China, from contact with the Islamic Middle East, from contact with the New World, and begin to fold that into this new sort of scientific thought that will really change the way we view science. It really calls into question what we knew, what we didn't know, what we thought we knew, which we find out to be all wrong. The thing that we're going to talk about today is really the beginnings of the scientific revolution, and that is kind of the calling into question the world as we know it. If you went back to the Middle Ages, the medieval view of the cosmos really was very limited. We thought that the Earth was made up of four elements: earth, wind, fire, water. Your body was made up of four fluids, four humors: the yellow bile, the black bile, blood, and phlegm. These date all the way back to the Greek origins, date all the way back to the Greek thinking of Aristotle and then later Ptolemy. The When you looked at the Earth was the center of the universe, and everything revolved around the Earth in these perfect circles, unchanging heavens that were all centered on the Earth. This was the accepted worldview, and it was the view that was supported by the church. But during the scientific revolution, this is going to begin to be called into question. Observation, new tools, new thought, mathematics are all going to start bringing this into question. So you go back to the Middle Ages, and this is what you saw. Okay, the Earth as the center of everything, and everything else revolving around that Earth, unchangingly. Okay, the Aristotelian view of the universe here. You can see the moon, Mercury, Venus, right? The sun, Mars, Saturn, Jupiter. Okay, and out here you get into the firmament, which is the place of the stars, and you can see the stars in this level here, unchanging. But when you start seeing the beginnings really of science, and especially astronomical science and physical science, this all gets called into question. Guys like Copernicus and Brahe and Kepler and Galileo are all going to really change this. All right, Copernicus was really a mathematician. Copernicus lived 1473 until 1543, and he was observing eclipses, and he couldn't figure out why his mathematics wouldn't work. So he starts trying to figure out why these eclipses aren't working out mathematically, why he can't predict them mathematically without building in all sorts of corrections. And what he stumbles upon is that our model is wrong. And Copernicus proposed that in reality, the universe, or at least our universe, was heliocentric. Everything revolved around the sun. When he put the sun as the center and had everything else revolving around the sun, his math worked. And so in 1543, when he published on the revolutions of the heavenly spheres, that's what he's saying. Now, the only problem with that is that he's going against the accepted view of the church, and immediately his work is attacked. But here's the thing: the printing press has already been invented. And so others can gain access to his work, and they do. And they start to either try to prove him wrong or prove him right. The Copernicus, as you guys can see here, stuck the sun here and had the Earth and the other things the other parts of the universe revolving around the sun. That's why we call it this heliocentric view. The old view, geocentric, earth-centered. The new one, heliocentric, sun-centered. Galileo, using tools like the telescope, would begin to observe the heavens. He would communicate with other people, like even Kepler, who we'll talk about in a minute, and they believed that Copernicus was right. Galileo observed things like the moon. He observed moons on Jupiter, and he finally concluded that these moons orbited planets, and that the really the universe was not unchanging. When you look at the moon, it's not perfect. It is pockmarked. It is hammered with craters. If you look at Galileo's writings on Jupiter, you can see his observations here, where he's trying to figure out what things are going on around Jupiter. And so, what we kind of using the telescope like this, and so what we finally kind of understand here is that these guys are using new tools, new science, new observation, mathematics, same things we use today when we talk about science, and that they're figuring out that maybe, just maybe, the model that we've been using for so long is wrong. The more scientific challenges come from Johann Kepler, who will use the observational data collected from a Danish astronomer named Tycho Brahe. Brahe was fascinating, by the way. If you ever get a chance to read about him, read about him. He he was a little bit crazy. He gets involved in a fight when he's in school. He gets his nose cut off in the fight, so he wore a, according to a lot of sources, it was silver or gold, but in reality, most people think it was brass, prosthetic nose. But Brahe collected this huge amount of observational data that Kepler will then use to put the math to. And Kepler, using Tycho Brahe's our observation, will discover essentially that planets are not doing what we thought they were. That Kepler's laws say that planets speed up and slow down, that they go around the sun in an ellipse, not in a perfect circle, and that they speed up as they move towards the sun, and then they slow down as they move away. Kepler could express all this mathematically. And Kepler's laws of motion are still used today in physics, but he couldn't exactly figure out why. This guy does. Okay, Newton. Isaac Newton is the most important figure in the scientific revolution. Newton puts it all together by bringing together the studies of Copernicus and Kepler, the physics of Galileo. He will put all of it together and essentially lock himself up, come up with the math that he needs, which is essentially the calculus. And you guys, if you take calculus, don't use Newton's calculus. You use a calculus invented by a guy named Leibniz. But Newton just needs the math. He doesn't necessarily care about the beauty of math. He needs it to get to get an answer. And by putting all that together, what he comes up with is this model that he can express mathematically. It's a comprehensive model. And what essentially it gives birth to is Newton's view about the universe is the mechanical view of the universe. The universe works like a machine that has laws. He expresses all this in 1687 in the Principia Mathematica, okay? The natural philosophy, mathematical principles of natural philosophy, which in Latin is called the Principia, and published in 1687. And this is everything. This is Newton's synthesis. And really, what it kind of does is it calls into question a lot of these things. That if the universe works like a machine that we can understand, that we can unlock, that we can express mathematically, then what place does God still have in this? Now, Newton never believed that God had left the universe. Newton believed that God had to have set this up because it works so perfectly and can be expressed mathematically. But when you go and take a look at Newton's laws of motion, which all of you have heard before, every object at rest stays at rest, objects in motion stay in motion, force is equal to mass times acceleration. If you've ever taken physics, that's the key physical equation that you use all of the time. For every action, there's an equal and opposite reaction. But this is the centerpiece, the law of universal gravitation. Gravity is the force that's making the planet speed up and slow down and move in ellipses. What holds us here to the Earth. So he can express all of this mathematically. Now, the scientific revolution is also a part of a growing world. The Spanish have made contact with the New World. They've started to catalog some of the things that they have seen in the New World, new plants, new animals. The Really the ideas of or the exploration of the Spanish leads others to begin to look at the biological world around us. And Linnaeus will develop a system that we use to classify the plants and the animals. It's still in use today. So science is becoming really something that you are familiar with. Today, if you've taken a science class, you know all about the scientific method that you form a hypothesis, you deal with the observations, and you try to see if that is that really works. Bacon and Descartes here, okay, Francis Bacon and Rene Descartes, they are the ones that really give us the scientific method today. It's really today's modern scientific method is a mixture of Bacon's inductive reasoning and Descartes' deductive reasoning. Bacon would really kind of formalize this method of inductive reasoning, where you demand evidence through observation and experimentation rather than just speculation. The Descartes is famous because he creates the deductive method of reasoning, removing all doubt. Descartes really thought that you had to remove everything to the point where that really the only thing that you can be certain of is your own existence. And once you get to that point, then you can build up knowledge back. And for him, geometry, mathematics are the foundation of knowledge. And that is, of course, today one of the ways that we express things scientifically through the use of math. The the rest of the part about the scientific revolution deals with the works in other places, Robert Boyle, chemistry, the William Harvey, the circulation of the blood, Vesalius's dissection of humans, and other things as well, dissecting human bodies, so discovering the structure really of the human body. So the scientific revolution, in a lot of ways, challenges the accepted worldview, the one that is accepted by religion as well. Many religions, including the Catholic Church, will ban many of these books. Catholic Church put Galileo on trial in 1633 for heresy. He was really spends a lot of time on house arrest. This whole idea of the sun-centered universe really was called into question. But remember, the printing press has allowed these ideas to get out and to be challenged. And when you can back things up mathematically and others can do the math and come up with the same answers, then you have to kind of tip your hat to some of this. And even though it's challenged, it becomes the foundations really of the scientific revolution. All right, we're going to stop here and I'm going to put up another video about the scientific revolution's influence on what happens next, which is the Enlightenment.